Thank you. So this morning we have talked about the function field setting, and we have observed some similarity between number field and the function field. Also, we have observed some differences. So in the afternoon, I would like to introduce the notion of adelic curves. So that notion is a core notion of the joint book with Moriwaki Sensei. So it's somehow not. So it's a notion that has already been considered by other authors or other people, but we have studied the geometry of numbers, like what you have seen in previous lectures. So today I have no time to begin with the geometry of numbers part, but I will give you a definition of adelic curves and some basic properties of such objects. So our aim is to provide a uniform treatment for geometry of numbers. So not only usual algebraic numbers, but also, for example, function fields. Also finitely generated fields. Q, and also trivially valued field excitation. So I will first give you the formal definition and provide you some examples. So first section I will give you a definition. So the notation, I will give you some notation. So K is just the field. I have no restriction to the field. So Mk is a set of absolute values. So there is a slight difference between Mk and the sigma k for the case where k is q. So here we consider all possible absolute values, not only equivalent classes of absolute values. So therefore, for each equivalent class, we consider all possible absolute values in the same class, and we just consider Mk as a set of absolute values, or K, of course. So we call adelic curve. So the data S is K omega A nu and phi, where K is just the field. And secondly, omega A nu is a measure space. And the third condition is that phi is a map from omega to mk is a map. So for every element in omega, we associate an absolute value of field k. So usually phi omega is denoted by absolute value indexed by omega. So you just consider a family of absolute values on the same field parameterized by a measure space. So such that so for any element in K, maybe no zero element in K, so the function omega goes to the absolute value of A with respect to the absolute value indexed by omega, and I take a logarithm. So this one is immeasurable and also new integral. That's require that if you evaluate log of the absolute value of any non-zero element, you obtain an integrable function on omega. So if in addition for any A in K which is non-zero, the integral of omega of this function is 0. So we say that S is proper. And this formula is called a product formula. So you will see why it's called like that. So some historical remark. So this notion has also been considered by Gubler. But he called it somehow like M field. And also globally valued field. Of Yakov and Ryszowski. So the work of Gubler, he considered that some height theory and also Nivalina theory. The work of Yakov and Ryszowski, they consider some model theory about the field. So although similar notions are considered, they have very different motivation. So it's not complicated to give the definition, but so to understand why this definition is interesting, I need to provide some examples. So the first example is that we fix a field K that absolute value with index 0 be the trivial valuation. Okay. So then we can take an arbitrary measure space. And we take a phi, be the map from omega to mk, which sets every omega to the trivial absolute value. So then you get adelic curve. So k omega in u phi is a proper adelic curve. So reason is that if you evaluate this function on the absolute value function on some non-zero element in k, so you obtain 1. If you take a logarithm, you obtain 0. So the zero function, the constant zero function is so measurable on omega and integrable with integral 0. So it's a proper adelic curve. So this, in some sense, the most simple one. Okay. Then we can consider number field. So if you are not that familiar with algebraic number theory, you can just consider the particular case Q. So let K be a number field. And omega K is the places of K. So it's just the set of equivalence classes of non-trivial absolute values of K. So maybe I just write omega. So let A be a discrete sigma algebra of omega. Just every singleton is considered to be measurable with respect to A. Okay. Now, for any element in omega, so we take an absolute value in the class omega. So which extends either the usual absolute value on Q. So if it is Archimedean, and if it is not Archimedean, then we suppose that this absolute value extends some periodic absolute value on Q. So in particular, if you compute the absolute value of P, you find P minus 1. So if this absolute value extends the periodic absolute value on Q. Okay, then I get a map from omega to mk, because for each class I pick one representative in the class. So it remains to introduce a measure. So that nu be the measure. So since I consider the discrete sigma algebra, so I only need to precise the measure of each point. So I suppose that nu of omega is the dimension of the completion k with respect to omega with respect to the completion of q. So so I complete k and q with respect to the same absolute value, and I compare their size. Now you have the usual product formula. Saying that for any a in k which is non-zero, you will have the product of omega in omega, the absolute value a to the power k omega over q omega is 1. So you can rewrite this equality as somehow the integral over omega log of a omega with nu d omega is 0. And therefore you get an adelic curve which is proper. So of course the choice of the measure is very important in this example. So if just in case you are not familiar with number fields, you take Q and you observe that you have some product formula which is simpler, and then you got an adelic curve corresponding to Q. Okay, so of course function field is one of the examples. So I would like to be a little bit more general. So I consider function field of higher dimensional variety. Okay, so that k, small k be a field. X be a normal. Projective. So here normal names integral and normal, so maybe integral scheme of dimension d, which is at least 1. So for example, you can consider some regular projective curve. So it is also an example also of a spec k. And now I take k as the field of all rational functions on the scheme X. So omega is x1, which is a set of prime divisors. So here I assume that the scheme to be normal, so there is no difference between Cartier divisors. So there is correspondence between Cartier divisors and Huayi divisors. So in the curve case, you just consider the set of so closer points in the curve. So A is discrete sigma algebra. So we also fix a family di. So I from 1 to d minus 1 of ample divisors x. So just a word about a curve case. In curve case, you have an empty family of ample divisors. You don't need to consider ample divisors. So, but for higher dimensional variety, you need to take some auxiliary ample divisors to have a good structure. And then that new little measure. So on the measurable space, such that okay. So for any y in omega, which is prime divisor, so I need to consider the measure of this one element set. So is this defined as the degree of the intersection product d1 and the d minus 1 with the cycle of y. So just one word in curve case. So nu of one closed point is just the degree of kx over k. So in this case, you don't need to consider the intersection product with the auxiliary divisors. Okay. So it remains to define the map from omega to the set of absolute values. So then this procedure is very similar to what you have observed in the morning for the curve case. So given a point, you can consider the local ring of the scheme at your point, your curve at your point. That is a discrete variation ring. So here the situation is similar for y in omega. So let OX y be the local ring. Of x, so maybe of OX. It's the generic fiber and the generic point of y. So since y is a prime divisor in a normal variety, so it is a valuation ring and the fraction field is K. So it will give you some valuation, which I write as Vy from K to Z union plus infinity. Okay, then we just take the absolute value indexed by y of the exponential minus vy point. Okay, then we have some product formula. So saying that for any f in K, which is non-zero, so you will have the sum for any y in omega is computer vy of f times this degree 51 d minus 1 in the section of y is 0. You consider the valuation of f times this factor, and then you compute the sum, you find 0. So, so that you get the integral of omega, so log the absolute value of f with respect to y, nu of dy is 0. So I'm sorry, so v is very similar to nu. So you get this property. Therefore, you have some adelic curve which is proper. So k omega a mu, and this phi. So sending y to absolute value indexed by y. So is a proper adelic curve. Okay. So in all these examples, except the first one, which might be a little bit artificial, you will see that it's quite natural, in fact. So we have some discrete sigma algebra inside the structure of adelic curve. So now I would like to introduce an example which is somehow interesting in number theory. And then you need to introduce some non-trivial sigma algebra to have a good structure of adelic curve. So that explains why we need something which is a little bit more difficult than just taking a sum. We need to take some measure. Somehow it's similar to probability theory. In first, so maybe in the first probability theory course, you learn discrete probability measures, and then you can do some computation. And then in some stage you need to pass to continuous models, and then you need measure space. So in order to be very explicit, I consider just one particular case of finitely generated field. So I take the field of rational functions with one variable. So this you can consider as a rational function field of so P1 over Q. So it's somehow about a little bit fancy to think such a field as a field of rational function. So as before, I take K as a notation of this field. But there are several types of absolute values. So you have seen that in the function field case of curves, so if you pick close point, then you get some valuation and also an absolute value. And then if you have some absolute value on Q, you can extend to an absolute value on K. And finally, you have some Archimedean part. So let me introduce three types of absolute values. So the first type. So for the closed point, x of P1Q. So you get some Vx variation. Okay. Okay. Now, so I need to pick a representative of the absolute value in this class, which is not the usual one. So let me explain the construction. So if x is not the infinity point, so x is in A1Q in the affine line. So this is just the P1Q excluding the point at the infinity. So then x corresponds to some polynomial fx in zt, which is irreducible in Qt, and with coprime coefficients. And now we can take some height of x. So it's exponential integral from 0 to 1. So log m of fx e 2 pi it dt. So this is another measure. Of x. So maybe of fx. So why this would be the height of the point? So let me explain another computation of this integral. So assume that fx is given by adt 2 power d plus etc. plus a1t plus a0. So which is written as ad times t minus alpha 1, t minus alpha d. And then we are integrating this function around a unit circle, and then there are some roots which remains inside the circle, some are outside the circle. And then you can compute this one as ad times the product of j from 1 to d max of 1 and alpha j by residue formula. So it measures the complexity of the irreducible polynomial with a coefficient in Z. Okay, so if x is infinity, you just take the infinity as the trivial absolute value. Does not consider the absolute value really inside the class. So in some sense you can consider this one as the absolute value, some absolute value inside the class corresponding to infinity but with power 0. Okay, so this is the first type of absolute values. The second type is something coming from the absolute value of Q. So for any p prime number, so we let this one be the absolute value okay, such that so for any polynomial which is ad t to power d plus a1t plus a0 in Q, so I consider not rational function but really a polynomial. So we take fp, which is the max for j in 0 to d to jp. So now it is a formal exercise to verify that such thing is transform the product of two polynomials to the sum, to the product of absolute values, and then extend to an absolute value on k. So this is the second type. Okay, and the third type is a little bit strange. So it comes from really some Archimedean consideration of this field. Okay, so we consider such set 0, 1 star. So it's defined as the set of elements t in 0, 1 such that the E of 2 pi I t is transcendental. So once it is transcendental, you can evaluate a rational function on this point, because it's never a root of a polynomial. So you are safe to evaluate a rational function on it. There is no problem. So for any t inside this set, so that this guy be the absolute value okay. Such that for any f in Qt, which is k, so the absolute value of f is given by the usual absolute value of f evaluated at this transcendental number. So as I had said, so there is no problem to evaluate a rational function if you know this guy is transcendental. So the point is that although I have excluded many points, because you have many points such that this one is an algebraic number, but in fact inside this set, the set of the t such that such one is algebraic. It's just a countable set. So in a sense of measure theory, no problem. So if you consider the big measure, you have just thrown out some measure 0 set. Okay, now I can define the adelic curve. So that omega h be the set of closed points of PQ1. So P is prime numbers. And omega is omega H union P, so disjoint union, and the disjoint union of 0, 1 star. So now I consider on this set discrete sigma algebra. But on this set we consider some Bldg algebra. So now you have disjoint union of 2 sets, 3 sets. So if you consider discrete sigma algebras on this one and this one, and Bldg sigma algebra on this one, so you get some sigma algebra on the whole space omega. So also we consider the measure or omega H such that the nu of omega is 1 if omega is inside the omega H and the P. And also the restriction of nu on 0, 1 star is just a Bldg measure. So now you have somehow all the data, so you have a measure space and with application, so and a map for omega to a set of absolute values. So for each element inside, you have a fixed absolute value. So it remains to check that it is an adelic curve. So you need to check the measurability and the integrability. So now with this very special choice, you can get a proper adelic curve as follows. So I remind that for any f inside K which is non-zero, you have an integral of log f omega nu d omega can be written as a sum of 3 terms. So first of all, you have the sum of x in omega h. So log of fx. So for closer points, you have this, and you have the sum of p inside p. So log of fp. And finally, you have the integral of 0, 1 star log of f e 2 pi r t dt. So you consider the Bldg measure. So since we have thrown out only countable points for the Bldg measure, there's no problem to replace 0, 1 star by 0, 1. So just we consider the integral on the whole space. There's no problem because we just add a countable number of points. And now, in a particular case, where f is inside kt, inside the polynomial ring. Sorry, so here it would be Qt. So f can be written as f is equal to a of fx1 r1, etc. fxn rn, where x1 to xn included in this omega h, maybe which is not infinity. So anyway, the infinity will not count in the sum because just take the trivial absolute value. So here your I is just the valuation of xi of the field F. Okay. So if you count the sum of log of fx, so you just obtain somehow minus sum of x inside the inside the omega h. Excluded the infinity, so you have h of xi. Take a log of hxi, and to the power I. So you have this one. Okay. So you have also this guy. So now these fx1 to fxn are all polynomials with coefficients in z, and such that the coefficients are coprime. So if you compute the product of periodic absolute value, you just obtain 1. So finally you get the product of p. So the sum of p inside p log of ap. So you have the product formula saying that this is just a minus log of the usual absolute value of a. And finally, what is this integral? So this integral log of f e to pi I t dt is just the log of a plus the sum for I from 1 to n I the integral from 0 to 1 log of f xi e to pi I t dt. So you observe that this is just a log of the Malon measure. So this one is just a log of h xi. So now if you put the sum of this term, and this term together, you obtain 0. And so you get a proper adelic curve. So we can do a more general thing with an arithmetic variety, with some polarization, suitable polarization, exactly like in the previous case of a projective variety with some polarization. So for the archive setting, you have some variation coming from the choice of geometric polarization, so that corresponds to the first type of absolute value. So they are horizontal, in some sense horizontal. So a contribution of such polarization, and then you have some vertical contribution coming from each point in the base. So how to say, each non-Archimedean places of the base number field. So that corresponds to the second type here. So here you have some absolute value of the number field downstairs, and it will give rise to an absolute value here. But which is special is that we cannot just have one raisement of the usual absolute value. So at the infinity part, you cannot fix just one Archimedes absolute value. You need to take a continuous family of absolute values. So for this reason, you have the third type of absolute value coming from the absolute value at the infinity of the base field. So here the base field is Q, so you have the usual absolute value, but you need to change the polarization, otherwise you could not recover the product formula at the end. So for this reason, we do need some measure space. So of course, you can take another point of view, you take some topological space with Borel-Simon algebra, and then you can do a similar thing. But so in some sense, it's more convenient to consider measure space, because if you have a family of measurable functions and you take the limit of the family, you automatically get some measurable function. But for continuous function, so you need some stronger so how to say, conditions to ensure that your limit function is still continuous. So in this sense, it's more convenient to consider general measure space. Okay, so I will not explain the setting of Arakelov intersection theory, but you need to keep in mind that we can have more general examples. Okay, in the rest of time, I will explain the algebraic cover of adelic curves. So the idea is to show that for any adelic curve and any algebraic extension of the underlying field, we can construct some natural adelic curve structure. So this is very important in the study of height function, because you need not only to consider height of rational points, but also algebra points. And then you need some height function for in general. So I think this point has also been considered by Gubler, but seems that he needs some extra conditions. But here we can prove that such construction exists in more general setting. So let me erase this example. So in this section, we just fix some adelic curve. And we fix also an algebraic extension . Okay, so the purpose is to construct some measure space with some map, not for K but for L. So there's a very natural construction, and we take ML as a set of absolute values. L. And then you have a map for ML to MK. Just if you have some absolute value, namely phi, you can send it to a restriction of phi. Okay. And now, so it's just a restriction to K. Now you have such situations. You have ML to MK given by the restriction. Then you have, in the structure, you have a map from omega to MK. So since you are familiar with algebraic geometry, so if you observe such a situation, quite natural is to take the fiber product. of omega and L, and you get a set omega L. Okay. So what is the explicit construction of omega L? So omega L is just the disjoint union of M L omega for omega in omega, where M L omega is just a restriction to k minus 1. So the 1 point set absolute value omega. So you consider all absolute values on L with restriction on k equal to this absolute value. And you put all such sets in the disjoint union. That will give you the omega L. So then the map, so you have a projection here, so pi L to k. So pi L to k, so pi L over k, sorry, sends every element omega, so sends every element x in m omega to omega. So that's very simple. And you have also another projection, so which is phi L. So this phi L will play the role of phi in the new adelic structure. So in the setting of sets, it's very easy. So now what we need is to define a sigma algebra and also a measure on the measurable space. So we need to define AL and mu L. From AL to maybe union infinity. Okay. So for AL, it's very natural. So maybe just to give a different construction. So AL is just taken as the smallest sigma algebra. So making pi of L over k, so you need this map to be measurable, and also other functions and functions x in omega L to ax. So here a is inside of L for all these functions measurable. So if you are familiar with probability theory, then it's quite natural. You have a family of random variables. You can take the sigma algebra generated by these random variables. So you have just some maps, some functions. You need to take the sigma algebra generated by such maps and functions. So why we need this? Because to construct an adelic curve, we need such function to be measurable. And to compare the structures, we need a projection map to be measurable. So then, for defining the measure, one so one possible way is to construct some fiber integral of such a fibration. So namely, we try to construct some measure on this fiber space, and then the whole measure is given by firstly the integral along the fibers, and then another integral on the base space omega. So that is the idea. So okay. So we will define omega in omega a probability measure. So P omega on M L omega. So we will construct a probability measure on this space. So now, so here, if this extension L over K is a finite extension, suppose that this extension is a finite, then you have only finite many possible elements inside this set. Then you can construct some discrete probability measures that I will explain a little bit later. So now for the infinite case, what can you do? So you have an algebraic extension which is not finite. Then you can write it as some projective limit of finite extensions. So now you have also a tower of extension of absolute values that can be written as projective limits of finite sets. And of course, as you know, in measure theory, projective limits is not that well defined. The reason is that if you take finite pieces of measure space, and then you can construct their product, so you can do Fubini's theorems, etc. So that's quite natural. But if your number of space is infinite, then you would have some problem, because if the mass is so total mass is larger than 1, and then if you take the product, then it will surely explode. But for probability measures, there is no problem. So for probability space, you can take any copies of a probability space and you take the product. So that is very important, because in probability theory, you need sometimes to consider many random variables, especially when you consider some limit theorem. You take a huge probability space, which is a product of so many copies of probability space, that will not cause any problem. So in probability space, you can, in some sense, construct a projective limit, because you can construct some product and there's something inside. So then I only need to consider the finite extension case. Of course, there are some technical tasks to do. After that, after finishing the finite extension space, you need some hard work to do. But it's possible because you are considering probability spaces. So you really need to construct the measure fiber by fiber, because the fibers behave very well. So they are inside the category of probability spaces. Okay, so let me explain the fundamental case. Is that L over K is a finite separable extension. So why I can put a separable? Because you can write a finite extension as firstly a finite separable extension, and then a purely inseparable extension. For the purely inseparable case, you have just a unique extension of absolute value. So you can take some power, and then you are inside the smaller field, and then you have no choice. And then you just keep the same measure space. So you don't need to consider infinite, so inseparable case. Okay. So now I can explain the construction of the probability measure. So of course, the natural choice is that P omega is the sum of x inside n omega. So the degree of Lx over k omega divided by the degree of L over k and delta x. So this is a direct measure. So namely, so this guy is just the measure of the one-point set x. So now for the finite separable extension, you have some, in some sense, product formula. So you have the sum of x in omega in m L omega. Lx over k omega is equal to L over k. So this is a classical result in algebraic number theory. So I will not explain the proof, but you can find the proof easily in any classical literature on algebraic number theory. So this is the probability measure because the total mass is 1. Okay, now if you have a function any function. So here I don't need any measurability to define the fiber integral because the fibers are discrete. So we can define a fiber integral. So I L over k of f as a function from omega to r. Just I L over k f invariant on omega is the integral on such space M L omega. So f of x integral with this probability measure. So maybe it is not that easy to understand by the integral, but I would like to say that it's just the sum of x in m omega. So the coefficient Lx over k omega divided by L over k, and we will compute the average of f. So in some sense, it's somehow an average value of f. So some very easy properties of this construction. So there is some adjunction formula so for any omega, so any phi, sorry, for any function which is defined on omega, So you can consider phi composed with pi L over k. So to obtain the function on omega L, and then you multiply by f, and you compute L over k of this one. So in some sense, you just in this formula you multiply this by phi of omega, so which does not depend on x. So you can put the phi omega here. So finally you get to phi times I L over k f. You just take you have this this formula. Okay. And also, for an AB in L, if we choose 0, if you take a dimension of L over k, so multiply by I L over k of the function log of b point. So here the variable is here. Then what you get is the log of the norm of, so the absolute value of the norm of L over k of b point. So it is somehow you replace this fx by such log of b with respect to x, and then there is a classical fact in algebraic number theory which gives you that the average of this one is just the norm over omega. So this is also very important. So why it's important? You can imagine that afterwards I will define the integral of this function, and the integral of this function will give you 0 if the initial adelic curve is proper, and then you get some proper adelic curve for the case of L. Okay. So now there is still an obstruction to define the measure. So our aim is to define new L as new L of some set A. So this is a set in AL as the integral on omega and the I L over k, the indicator function of A. So this is the fiber integral, and omega, and then with respect to new d omega. So I integral fiber by fiber, and I obtain a function on the base measure space, and then I integral along the base space. There is one serious obstruction, is that it is not sure that the fiber integral will provide you a measurable function. So you need a measurable, positive measurable function to define this integral. So of course the fiber integral is positive, non-negative. It's pointwise non-negative. But it should be measurable, otherwise we cannot compute the integral. So you will not have the expected expected property like the additivity or something, sigma additivity, etc. So for having good property to define a measure, you need this function to be measurable. So that is the main purpose of the following theorem. So if f from omega L to R is AL measurable, then the fiber integral of f is A measurable. So with this theorem, you can define a measure on omega L by using this formula. So it would be sigma additive. Okay. So in the remaining time, I will explain the idea of the proof. So you have already seen that if we replace f by 1, so you just integrate something from the base measure space, and then you obtain phi. If phi is measurable, then this integral is fiber integral is measurable. So for something from the base, there is no problem. And the sigma algebra AL is generated by this pi and some other functions. So it suffices to check that I of L over K. So some FA is measurable if for FA of the form x in omega L maps to the absolute value of A with respect to x. So you need to consider just this case. And we can also suppose that A is a primitive element of the finite separable extension L over K. So in theory, you need to check the measurability for every A element of L. But with some efforts, you can show that you can reduce the problem to only consider primitive element. So I take the minimum polynomial. Of A and alpha 1, alpha D, its roots. So you see that so these are Gauss objects of point A by the Gauss group of K. So now you have some expression saying that lambda K is just the sum of I1 to IK. So alpha I1 and alpha IK. So we have this expression, and the lambda K belongs to K. Okay. So now what you can see is that if you take a symmetric polynomial and you evaluate it alpha 1 to alpha D, you get something which belongs to K. So I just give this fact. So if f which is in K of x1 to xd. So it's invariant by permuting variables. Then you can find some other polynomial x1 is d such that f of 1 to alpha d is given by g of lambda 1 to lambda d. So this is a fundamental theorem for symmetric polynomials. So you have the ring of the algebra of symmetric polynomials. Then it is a polynomial ring generated by a symmetric polynomial of this one, this form. So then you get something which belongs to k. So if you have a symmetric polynomial, you evaluate at alpha 1 to alpha k, you obtain something in k. So in particular, the consequence is that so for any n, if you take alpha 1 n, power n plus etc. plus alpha d to power n, you get something in k. Okay? So now I give some notation. So for any omega in omega, we fix some embedding of the algebraic closure. So this is algebraic closure. So I embed this. I embed this inside the algebraic closure of k omega. Fix an embedding. And then extend so the absolute value of omega to k. So you have so many choices, but I just fix one. So I fix one choice of extension of this absolute value to k. And that S1 omega, etc. SD omega be the sorted sequence of so the absolute value of 1 omega and alpha d absolute value omega. So here I have a fixed extension of this one to k, so I can evaluate the absolute value of alpha 1, alpha d. I just fix the sorted sequence of this sequence. So namely, I require that S1 of omega is bigger than etc. bigger than SD of omega. Just fix some configurations. So now what you can see is that I can write the fiber integral as some sum of SI. So I over k of FA evaluated at omega, so it's just the sum of x inside omega L. So M L omega. So fx is the absolute value of xa. Okay, so this is just 1 over d. So because d is the degree of L over k. And then I take the sum for I equal to 1 to d. So alpha I omega. So because so if you count the multiplicity, so all these possible values are given by the absolute value of alpha I. So you give the absolute value with different extension is given by the gamma orbit if you count the multiplicity. And then since I take such thing as a sorted sequence of this one, so you just get the average of the SI. Now it remains to prove that SI, in fact, they are measurable. So it remains to prove that SI are measurable, functions. So then I need a very classical lemma in mathematical analysis. So that beta 1, the beta n, and be elements in K. So one has max of J, absolute value of beta J omega, as the limit sup of n goes to the infinity, the sum of 1 to n, beta I to power n, omega, then 1 over n. So I think it becomes a very classical exercise if you take the usual absolute value in R. Then it's something that you are familiar with. So I have no enough time. So I just explain the idea of proof. So of course in a classical case you have some direct proof, so you don't need to follow this way. But so the idea is that we can assume so beta 1, beta L, which is bigger than 1, than beta L plus 1 omega, etc. So you can assume this without loss of generality. And then you take a gamma I, which is beta I over beta 1. Then you have gamma 1 is 1, and gamma I is 1 for I in 1 to L. And afterwards, the absolute value of gamma I is smaller than 1. I is bigger than L plus 1. So the important technique is to consider this identity. So you consider gamma 1n plus gamma ln. So then gamma 1 and plus 1 plus gamma l and plus 1, etc. Gamma 1 and plus l minus 1 plus gamma l and plus l minus 1. So this is a matrix, Vandermonde matrix. Multiplied by gamma 1n, gamma l. So you have a vector like this, and if you multiply by this matrix, you obtain another vector that you are interested in. So now you consider some norm on Ka omega. Okay, so I need to take some completion of algebraic closure, something like that, to have some complete field. So just Z1, ZL as a max Zi omega. So this is a norm. And the point is that the norm of this vector is 1. And then you have some invertible matrix. So the norm of this vector, so it's bounded from below by some constant. So then that will give you such equality. So I will not go into the detail because I'm lacking of time. But you can continue with this idea, which also holds for our case of R. Okay, so what is the consequence of this idea? So I keep, so I will erase it. So let me explain that such thing. Will permit to write your function S1 here. So S1 omega. Here is just the limits of n goes to the infinity. So alpha n 1n plus etc. plus alpha d to power n and 1 over n omega. And for all n, this function considered as a function of omega is measurable because you have some element in k. So if you have some element in k, by definition, this is a measurable function. And then you have a limit of measurable function, which shows that S1 is measurable. If you apply the lemma. So for general, you need to apply the lemma to the family of alpha I1 times alpha ik with 1 smaller than I1, etc. ik smaller than d to obtain that S1 times Sk is measurable. And so if you know all these products are measurable, you get that Sk is measurable for all k. And then so you get the desired result. Okay, thank you very much.
Okay, so do you have some question, comment?
This is not essential, but S1 is lim sup or?
Oh, sorry, lim sup, yeah, I'm sorry. So maybe it's possible to prove that it's a limit, but I have not tried. Because the limit sup is sufficient to prove that it's measurable. Yeah. Thank you.
Okay, so thank you.
Thank you.